Sim. Boa tarde a todos. Espero que se encontrem muito bem. Obrigado por comparecer nesta apresentação. Nesta oportunidade, teremos o prazer de escutar ao Dr. Gianluca Vella, que irá apresentar o tema Uma perspectiva sobre a capacidade de retenção de água dos rejeitos de mineração de fluorita não saturados. Gianluca Vella possui doutorado em engenharia geotécnica pelo Politécnico de Torino, Itália, em 2017. Desde 2018 atua como engenheiro geotécnico no PINI Group, na Suíça. E a partir do ano 2024 tornou-se professor na Universidade de Ciências Aplicadas e Artes do Sul da Suíça. Sua pesquisa se concentra principalmente em liquefação estática, ocorrência de estados críticos, envelhecimento e caracterização de rejeitos em condições não saturadas. No âmbito profissional, trabalha em projetos internacionais envolvendo projetos de túneis em condições complexas, estruturas de contenção, fundações, monitoramento e análise de estabilidade de taludes. O Dr. Vella participa regularmente como autor em conferências nacionais e internacionais voltadas à mecânica dos solos e das rochas, com mais de 60 publicações. Welcome, Gianluca. Thanks for this invitation.
Hi, Gino.
Please feel free.
Okay. Good afternoon, ladies and gentlemen. It's a pleasure for me to be here to hold this lecture titled An Insight into the Water Retention Capability of Unsaturated Fluorited Mining Talings. Well, these lectures aims to provide an insight into the water retention capability of the Stava tailings collected from the Presteval Fluorite mine that failed in 1985 in Italy. The focus, the objective of this presentation will be the evaluation of the water retention curve as a key tool for tailings characterization and, of course, for interpreting some peculiarity of the unsaturated soil response. We have just a look at the index. First of all, an introduction. Then I will provide you with some basic concepts about the unsaturated soil mechanics. And then the third chapter is devoted to describe the case of Stava tailings, in particular the event, the geomechanical characterization of the tailings, the experimental apparatus I used and the testing techniques, and I will describe the experimental results with some comments. Then I would like to present some additional application, in particular how the water retention curve has been used by me and my other colleagues to interpret the volumetric soil response of tailings and to interpret the deformability behavior of the soil. Then some conclusion will follow. So we can start with the introduction. What are tailings? Of course, tailings are the waste materials of a mining operation. They mainly consist of a mixture of silt, clay, sand, with usually a high content of metals, processed water coming from the mining operation, and chemical reagents. And they, depending on the solid liquid ratio, of course, they can show the consistency of a slurry, cake, or a paste. Tailing dams, as you know, are complex geotechnical systems that contain the the waste products of mining operation. So they mainly consist of a decant pond that we can see in the picture below, raised embankment, the dam that we can see here, and a transitional zone, intermediate zone, the so-called the beach. There are many different rising techniques for tailing dams, such as upstream, downstream, centerline, and so on. So this topic is quite large, and I will just show you in the introduction with some recall. Why is the stability of tailing dams is relevant, especially nowadays? Well, it is relevant because tailing dams are complex structures that are particularly prone to failure for many reasons. For instance, they are made of heterogeneous filled material. They are raised over a large period of times. Sometimes there are poor regulation governing the design criteria, and their large surface makes the punctual criticality identification quite difficult. So they require an extensive and continuous monitoring. Here we have an example on the right of some famous collapses. Here you can see the Stava collapse in 1985, the Meresprut in South Africa in 1994, the Aznacollar in Spain in 1998, and the more recent collapse, Mont Polley and the Fejao Dam some years ago. The analysis carried out by literature highlight that the historical trend regarding the number of failures is quite high. We can see that from this graph that there is an average of 2.5 failure or collapse per year. That it is quite a high number. The collapse of the structures result in casualties, environmental costs, and so on. And as we can see in the picture below, the tailings growth is estimated about 12 kilometer cube. So it is a very high quantity. And as we can see in the picture on the right, the main causes of failure are overtopping, static liquefaction, cyclic or dynamic liquefaction, and so on. So these structures are quite problematic and need a deep investigation. Here I resume the main causes of tailing dams collapse. As you can see, there are a collapse of tailing dams could be due to one or to a combination of many factors. I listed the main, for example, poor drainage, poor design, poor maintenance, seismic activity leading, for example, the dynamic liquefaction of the soil, foundation instability, erosion, slope instability, piping and seepage, or the structural failures, human error, or one of the most critical causes are the saturation of tailings and the change in water content. These causes are strictly related to the topic of this presentation. We can, as we can see in these pictures, wide surface area of tailings are exposed to atmospheres, which govern the position of the water table within the basin, as you can see here. So, leading variation in the extension of the unsaturated zone above the phreatic surface. So, the unsaturated condition mainly involves a large portion of tailings, and this is the cause we are dealing tailings in this lecture in unsaturated condition. In particular, the unsaturated condition involve a shallow layer because they are involved in the water exchange with the atmosphere, with the, for example, infiltration, runoff, evaporation, and so on. But partial saturated condition involves also deep soil layers above the water table, where the capillarity phenomena that we will see in next picture can occur. Finally, one of the most important cause of collapse is the static liquefaction. Considering the relationship here in the graph on the right between the degree of saturation and the Biscampton parameter, what can we say? We can say that in undrained condition, when the degree of saturation slightly decrease below the unit, for example, from 1 to 0.9, due to, for example, due to the change in suction, we have a big decrease in the B, and of course a big decrease in excess of pore pressure, as we can see from equation number one. So this leads an increase in the soil strength, and so it strongly influences the static liquefaction. In fact, as we have a small variation in degree of saturation, we have big variation in Biscampton parameter. We have a big decrease in the excess of pore pressure, so we have in this influence in a great manner the static liquefaction susceptibility. So this introduction to show you that a deep knowledge of the hydromechanical response of this kind of soil under partially saturated condition is of course a key tool to perform stability analysis of tailing dams. Okay, now we can proceed with some basic concept, with some recall about the unsaturated soil mechanics before showing my experimental investigation. So the soil can be seen as many capillary tubes having different diameter. If we consider, for instance, these pictures, we can see these different tubes, and here we consider the water table. Below the water table, we are under saturated condition, so the pore pressure is positive and the degree of saturation is 100%. Above the water tables, what we have? We have, first of all, a zone where where we have still fully saturation of the soil. This is the capillarity saturation zone. And then after a certain height, we have a partially saturated zone. In the unsaturated zone, the degree of saturation range between 0 and the unit. The pore pressure is negative and the suction is positive. We can say that it's worth to note that the height, the capillarity height, of course, is related to the diameter of the tube. Smaller is the diameter, the radius of the tubes, higher will be the capillarity height, and after that it depends also from the material, for example. So if we consider the soil as a group of tubes, we can see that we have a part above the water table. After a fully saturated zone, we have a big extended zone where unsaturated condition would occur. The capillarity is governed by the suction. By the suction is the total suction, and can be divided as the sum of osmotic and matrix suction. The matrix suction is mainly related to the fluid phase pressure and the mechanical interaction phenomena at the interface between water and air, while the second component, the osmotic component, is mainly linked to the concentration of salts and to phenomena of chemical interaction between the salts and the double layers of ions around the clay particles. In unsaturated soil mechanics, so we have three phases: the soil phase, and the void that it filled partially with water and partially with air. In unsaturated condition, the water in the contact zone between the grains gives menisci in a manner similar to occurs in capillary tube as described before, producing a state of compression that we can see here, the force P, between the grains. And these are great effects in unsaturated soil mechanics because it implies that there is an increase of the normal stress between particles due to this force. So an increase of the shear strength in unsaturated condition, and of course a reduction of binding occurrence. It's worth to note that there is a coupling between hydraulic and the mechanical response under unsaturated condition. Here we have a flow chart taken from a recent paper, where we can see that the water retention curve is strictly connected for evaluated hydraulic conductivity, for instance, so to assess water flow problem and to assess stability problem. But the water retention curve that I will show in a few minutes is a key tool, a very important tool for estimation of the unsaturated shear strength that in turn allow to deal with the stability problem. The stress variable in unsaturated soil mechanics are the following: suction and net stress, as we can see here, and or suction and effective stress. In unsaturated soil mechanics, over the years, many shear strength criteria were proposed. This equation we see just for simplicity two equations, but there are a lot of equations, and these equations are usually based on two different hypotheses related to the role of suction and net stress. For instance, the Bishop stress criteria and the Fredlund approach. In the Bishop criteria, we have the key parameter that is related to the degree of saturation, and this difference that is the suction. And this is very similar to the Moore Coulomb criteria, but there is these additional terms. So these additional terms is the apparent cohesion. So it is the contribution given by the unsaturated condition to the shear strength of the soil. Another formulation is the one proposed by Fredlund in 1978, and it requires more parameters because, for instance, it depends from the friction angle associated with the change in suction. Here a list of the shear strength criteria. I would not give some details, but just I would highlight that some of them depends on the soil mineralogy, other depends on the prediction depend on the water retention curve. This is the acronym. Other are based on the critical state soil mechanics. More recently, other Vanapalli et al. makes the use of the water retention curves and so on. Here, to show you that many shear strength criteria has been proposed during the year. So, what is the water retention curve? That is the topic of this lecture. The water retention curve relates the water content or the degree of saturation or the water ratio of a soil with its suction. The water retention curves, as you can see here, govern the transient of the filtration process together with the unsaturated permeability, and it is considered one of the most important properties of unsaturated soil because it can be used to estimate the negative per water pressure, I mean the suction, on the shear strength, permeability, and compressibility of unsaturated soil. So it can be estimated, as is the topic of these lectures, in several ways, such as laboratory tests, and can be, for example, can be obtained from odometer test, from suction control odometer test, or from grain size distribution curve. As I told you before, it is the water retention curve is the relation between degree of saturation and the suction. It is composed by two branches, the main drain branches, this one, and the main wetting branches, and there are some, due to hysteresis, there are some secondary branches. Depending on the degree of saturation, of course, the soil described by the water retention curve is saturated when we are dealing with the effective degree of saturation close to the unit. Then, following with the drying process, we have quasi-saturated soil where almost all voids are filled with water. Then we have the center part. Following with the drying, we have this center part in unsaturated condition where voids are filled both with water and both with air. And finally, this portion is the residual portion where the voids are filled with air. This curve is able to describe the drying and the wetting process of the soil, so the capability of the soil to retain water, and it is strongly connected to the capillarity, as I showed before, because above the water table we have a zone where the capillarity saturation is with a degree of saturation equal to 1, and if we represent this with the water retention curve, this head correspond to the higher entry values of the curve. So the point where after that the saturation of the soil assume very fast values less than 1. So we have the higher entry value as the minimum required pressure to desaturate a sample. There are many formulations to describe the water retention curves. The Brooks and Corey, for example, the famous Van Genuchten model and the Gallipoli model. So we have an experimental point, and we can decide which formulation is the best. Of course, there are a number of parameters to be calibrated different from one and the other formulation. Okay. After this short recall about the unsaturated soil mechanics, we can start with the describing what is my research and my experimental results. The result and the interpretation of this result that I will provide you is described in detail in some papers I published recently. For instance, this one, water retention behavior of tailings in unsaturated condition, and more recently this other paper that you can find more detail. So the soil, the tailings I investigated is the silty and the sandy fraction of tailings that are taken from the lower portion of Stava at upper dam, built one above the other on a natural slope near the city of Stava, we are in Italy. The two tailings dams were gradually raised in an upstream way to store the waste products, the tailings, coming from the separation process of the Presteval fluorite mine. Here we can see pictures of the tailings before the collapse. You can see the upper tailings dams and the lower embankment. We are in the northeast of Italy. What happens? We are on the 19th of July in 1985. The upper tailing dams collapsed on the lower dams that in turn collapsed, triggering the static liquefaction of the stored materials, and you can see a very big volumes of tailings, a mud flow, spilled out into the Stava valley. The mud flow traveled, reaching the Stava municipality, located at the south of the embankment. You can see here is the embankment. He destroyed this municipality. He continues his path, and he reached the city of Tesero. During his path, 268 people died. There were a lot of environmental damages and economical damage. The poor drainage, high phreatic levels, and unconsolidated states of the stored tailings are supposed to be the main factors leading the static liquefaction of these tailings. And the tailings I've tested were taken from the upper embankment here, more or less. First of all, the Stava tailings were characterized. As you can see here, there is a physical and chemical characterization of the Stava tailings. Here you can see the silty fraction, the continuous line, and the sandy fraction passing or not passing sieve ASTM 200. Here you can see the limit plastic Dattenberg limits, the hydraulic conductivity, and we performed some electronic microscope analysis on these materials, so that we saw that the silty fraction was made up mainly of fluorite and quartz. So the peculiarity of these tailings are little cohesion, little activity, and high specific weight. Okay, we test these tailings with a suction-controlled odometer apparatus. In particular, here I listed the sample we test. You can see the initial void ratio, the water content, the degree of saturation, the dry weight, and the initial stress. So we prepared the sample using different preparation method, different density, and different fine content to see the effect, to investigate the effect of these characteristic on the water retention capability of these tailings. Here you can see the slurry, and here you can see the compacted specimen, together with the different initial void ratio and together with different fine content. This is pure silt, and these are mixture made of sand and silt. The water retention behavior was investigated by means of different technique. First of all, the suction was imposed and the water content was monitored. So we used the axis translation technique and the vapor equilibrium technique. Or we adopted other tests where the water content was imposed and the suction was measured. So we adopted the dew point method. This is an example of the water retention curve that we obtain, in particular the points, the experimental points, the green points, due to the axis translation technique, the red points due to the dew point technique, and the blue points obtained with the vapor equilibrium technique. It's worth to note that we adopted these three techniques, but in literature there are many other techniques that I listed in this table. The first technique we use, the axis translation technique. As I told before, we adopted a suction-controlled odometer cell. So the experimental points having a suction below 400 kPa were obtained with these suction-controlled odometers. This is pictures of the odometer I adopted at Politecnico di Torino to characterize the Stava tailings. And here we can see the main components. Here the cell, the LVDT apparatus, the water volume indicator, a water chamber, and the air trap. And on the right, we can see a scheme of such apparatus. What is the working principle? Different air pressure and water pressures are imposed to control the matrix suction, that is the difference between air pressure and water pressure. Then exchange of water inside and outside of the sample is measured, providing the degree of saturation of the sample. And this procedure is repeated by imposing different suction values, and so increasing the suction, increasing or decreasing the suction, so imposing drying and wetting paths to obtain many experimental points to describe, to fit the water retention curve. This is an example of what we did. We measured the water volume of the sample at each step. The water volume change allowed us to compute the degree of saturation. You can see the formula, and then associating the degree of saturation with the suction we imposed at each step, both for drying and both for wetting, we obtained these green points that are the first point of the water retention curve. This is the apparatus, the sample, the dimension of the sample, and the preparation technique of a sample tested in such a way where the static compaction with using this frame or remolded specimen. The second technique we used for obtaining the water retention curve was the vapor equilibrium technique. This, so the experimental points with the suction up to 70 MPa were obtained with this technique. The vapor equilibrium technique is a method allowing controlling the relative humidity to impose a certain total suction. The total suction was imposed by creating a controlled humidity condition in a closed box and using a chemical solution. This condition, as I told, are obtained in a sealed glass container with a support in order to hold the sample. Inside the box, we have a chemical solution. The total suction within the specimen is obtained due to a net water exchange between the liquid phase and within the unsaturated specimen and the vapor phase in the box until the equilibrium between the two phases. So we adopted different chemical solution to obtain different total suction that are listed here. Here pictures of I just explained. We can see the sample suspended. Here the chemical solution, and this is the closed box. Again, this technique was used at Politecnico di Torino. Finally, the dew point technique was applied together the previous two techniques to obtain more data. Psychrometers was used to measure the total suction. The measuring of the total suction by using the dew point technique mainly consists in equilibrating the vapor phase of the water in the air space above a sample, again in a closed chamber, with the liquid phase of the water within the unsaturated specimen. A cooling system, we will see the picture in the next slide, is used to cool a mirror until some dew forms. So an optical sensor is adopted to detect the formation of this dew on a mirror, while a thermocouple attached to the mirror measures the dew point temperature. In the meantime, the temperature of the sample is get with a thermometer. A fan is also used to circulate some air and speed up the vapor equilibrium. So both the soil sample temperature and the dew points are used to get the relative humidity and to obtain the total suction according to the psychrometer law that you can see here. Here a picture again of this apparatus that I use at Politecnico di Torino. These pictures gives you an idea of what we obtained in terms of water retention curve. The green points with the suction control odometer, the first technique, and this point with the other two techniques, the vapor equilibrium technique and the chill psychrometer method, together with the main drying branch here, the main wetting branch, the scanning curve due to hysteresis phenomena, and the air entry value. This is the water retention curve, an example of what we obtained, for instance, for Stava silty tailings with initial void ratio 0.7. Let's proceed with the results. The influence, we studied the influence of the density on the water retention curve. This condition is a practical relevance in modeling the hydromechanical response of tailings, because this could represent different depth that you can see here at the same distance from the embankment. So at different depth, we have this different void ratio. So the effect of the initial void ratio on the water retention capability was studied by fitting the experimental point that we see before by using the Gallipoli model. This is the equation, is one of the model proposed in literature, and this model has the advantage to depends on the density of the soil. This is all the parameters required to be calibrated. Here we can see the main drying and the main wetting water retention curve of Stava sample. What can we see? We can see that a decrease in the void ratio shift the water retention curve to higher suction values, and this because the size of the pore decrease, so that higher pressures are needed to fill the small pores. This can be appreciated both for main drying and both for main wetting, and we have a good accordance of our result with literature data on, let's say, more standard soil. I mean, not tailings. Then we study the influence of the void ratio, fine content, and the sample preparation method on the air entry value. First of all, the effect on the density. Let's take a look at this graph where we have the air entry value and the initial void ratio. If we consider the effect of the density, we can follow these green arrows that is pointing up the behavior of this line, curved line. We can see that a decrease in the air entry value with a decrease of the density for statically compacted sample, the sample identified by the black triangles. If we analyze the effect of the fine content, the grading, we can see what happens in this red box. So the effect of the fine content on the air entry value can be observed by comparing the air entry values of two samples having the same initial void ratio, 0.7, but different fine content. This is pure silt, and this is the mixtures of sand and silt. We can see that a decrease of the fine content leads to a decrease of the air entry value. So a small pressure will be required to desaturate the sample if the sample is made of a mixture of silt and sand. Finally, we observe the effect of the sample preparation by, for instance, see this box. That can be the effect of the sample preparation method can be quantified by comparing the air entry value of a slurry sample, the circle 1, with the dotted line that is the interpolation for statically compacted sample. So if it is, how to say, if we have the same void ratio, but about 0.75, but different preparation technique, slurry, this one, and compacted. As the preparation method influences the soil structures, the air entry value of the slurry sample is higher than what predicted by the same sample prepared by statically compaction technique. We also studied the influence of the fine content on the water retention curves. Again, this condition has a great practical relevance since it can represent some depth, for instance, this section, but several vertical cross section with different distance from the embankment. This is because mainly due to the deposition technique. Close to the embankment we have tailings makes with more sand, and far from the embankment because of the deposition technique, tailings will be mixed with finer fractions such as silt. So the influence of the fine content on the water retention curve has been studied, as we can see in these two pictures, with main drying and the main wetting curves. An increase in the fine content, as we can see here, corresponds to a movement of the water retention curve to higher suction values. In fact, when increasing the fine content, the pores between the sandy grains get filled with these small particles, so resulting in a higher retention capability and a lower permeability. We also investigate the influence of the preparation method on the water retention curve. Here we have pictures of the slurry sample prepared with a water content equal to the limit liquid, and here we can see the sample prepared by the statically compacted technique. What happens also for the Stava tailings, the water retention behavior is influenced by the soil structures that in turns, of course, is influenced by the preparation technique. In fact, as we can see here, for example, the slurry samples show a greater water retention capability than the compacted sample, and this could depends on different side pore distribution of the sample obtained from the two different preparation techniques. So also the preparation technique has a great impact on the water retention capability of tailings, and this is observed also for other topics. For instance, the sample preparation greatly affects also the static liquefaction behavior, for example. Then we investigated the influence of the density and fine content on the shear strength of the soil. So the shear strength in unsaturated condition, as I said before, can be obtained by several techniques. For instance, the Bishop approach, where we have the apparent cohesion, highlighted in this red box, due to the effect of capillarity phenomenon. So this term, the apparent cohesion, decrease with the decrease of the initial density, as we can see in this graph. In fact, for instance, within the most common expected in situ density, as we can see, for example, in this red box, the unsaturated condition allow to gain an apparent cohesion about 10, 20 kilopascal. But this apparent cohesion will be completely, totally lost as far the saturated condition will occur. So we start from here and we arrive from here. We can see very well how the difference line corresponding to the different saturated condition are lowering with the lowering of the apparent cohesion, and so with the lowering of the shear strength. The apparent cohesion increase, we observe that it increases with the fine content, we assume for non-linearity, and the apparent cohesion decrease with the increase of the effective degree of saturation, as again, as we can see in these pictures, and it was published in this paper. Finally, we investigate the influence of the density and of the grain size distribution, so the fine content, on the hydraulic conductivity. We can say that the hydraulic conductivity can be obtained by the product between the saturated conductivity and the relative hydraulic conductivity obtained from the formulation proposed by Moalem, depending from degree of saturation and suction. What we can say? We can say that an increase of void ratio, for example, loose samples, move the relative hydraulic conductivity to lower suction range. Moreover, an increase of the fine content shift the relative hydraulic conductivity to higher suction range, as we can see on the right. So, if subjected to drying process, for instance, from here to here, looser sample or lower fine content unsaturated soils will show a lower hydraulic conductivity than denser or higher fine content specimen, as we can see from the the black line and the green line, where the black line has a higher void ratio, but after the drying process, it has lower hydraulic conductivity. Finally, we analyze the influence of the density and the preparation method on the pore size distribution. A microstructural interpretation of the hydraulic behavior of Stava tailings was carried out by assuming that the water retention behavior was due to the capillarity mechanism that is described by the Washburn-Laplace equation that is here, and we can obtain from this equation the pore size distribution. The influence of the initial void ratio on the pore size distribution on the statically compacted specimen allows us to see that the pore size density peak of the statically compacted denser specimen, the dotted black line, occurs at smaller pore radius than use of looser sample, this one, and that its curve, its PSD curve, is less wide than use of other three samples. And this suggests that the denser sample, silt with a weight ratio 0.5, has a smaller range of pore size, and this consideration cannot be done for the slurry sample. Okay, I would spend the last part of these lectures by showing you some additional application of the importance of the water retention curve in two cases. The first case is the interpretation of the volumetric soil behavior by using the water retention curve. Again, you can see this topic in more detail than I'm describing now in these works, my PhD thesis, and within this published paper written together with Professor Guido Musso from Politecnico di Torino. In this application involves an experimental campaign on suction control triaxial test to study the hydromechanical behavior of the same Stava tailings. And the hydraulic paths and volumetric soil behavior were accounted for the water retention curve, and confirming the coupling between hydraulic and mechanical response in unsaturated condition. Let's take a look of the apparatus we use. We use a suction control triaxial cell that you can see in these pictures. This cell is different from a conventional triaxial cell because allows to impose a suction at the specimen. So we are working with unsaturated specimen. And because of the unsaturated condition, the variation of the total volume of the sample and variation of the volume of the water are not the same. We are dealing with cylindrical specimen, 38 mm as diameter and 76 and 8, that were prepared at different water content and void ratio. Okay, here you can see pictures of the apparatus we use within the suction control triaxial cell to monitor the sample, the shape of the sample during the wool test. This laser are placed outside the cell, so they are not affected by changing temperature, pressure, and so on. They moving up and down to obtain the scanning profile of the sample. Here we have the list of the sample we test, in particular the monotonics triaxial test under suction control condition mainly consists of 3 phases. The first is the suction equalization through the axis translation technique. The second phase is the isotropic consolidation, and then the shearing. The third phase was performed by increasing the axial load and at a constant water content, that means undrained condition, or at constant suction, that means drained condition. Here we can see the initial state of the sample. We test several samples at different void ratio, water content, and in different drained condition. And here a picture of the one sample before and after the test. This test was used to evaluate the geotechnical properties of the Stava tailings, but within this presentation, they are used to show some peculiarity of these tailings under unsaturated condition. What we can say? We can say that the hydraulic path of test number 2 is given in these pictures within its water retention curve. I mean, the different test phases, triaxial test phases, are 1, initial state, 2, the end of the suction equalization, 3, the consolidation phase, and 4, this one, the end of shearing. The drying wetting path that occur during the shearing is represented, of course, by this line from point 3 to point 4. We can see that the entire stress path lies inside, completely inside, the water retention curve given by these lines, in which the drying and the wetting branch, the red and the blue, are evaluated at the different void ratio that are experimented by the sample during the entire test. So the water retention curve that we discussed before could be assumed a sort of domain, a region within the hydraulic path given from the triaxial test could exist. The entire stress path of all samples tested in triaxial test are given in these pictures, and again we can state that all the hydraulic paths are quite close to the degree of saturation, the dotted line reached during the test. And this is a way to say how that if the triaxial paths are plotted within a three-dimensional space, water ratio, void ratio, and the suction, it's clear how the water retention curve represents a three-dimensional domain in which all the stress path exist. We use the stress path, the water retention curve, also to evaluate other peculiarities in terms of volumetric strain. Let's consider the sample 0.7 initial void ratio, 60 kilopascal suction, and consolidated at 200 kPa as a net stress in undrained condition. The hydraulic path of this sample is given in these pictures. Point A and point B stands for the beginning and stands for the end of the shearing phase performed in a suction control triaxial cell. And in the same pictures, we can see the main drying water retention branches evaluated again for void ratio corresponding at the end at the beginning, and at the end of the test. First of all, since the shearing phase was performed under undrained condition, we have a constant water content. So the water ratio given by the degree of saturation multiplied the void ratio is a constant, and the stress path is basically a vertical line. The initial point A lies close to the main drying, and during the shearing phase, the sample exhibits a dilatative behavior. So the void ratio increased. The dilatative behavior is usually associated to change in water retention state toward the drying water retention surface. So it could be expected that the suction increase due to drying, but this not happens during our experimentation. We observed that the suction decrease. So how to explain this unexpected behavior? This could be justifying observed the water retention curve. So the importance of this concept in explaining the volumetric soil response. How to be justified? A decrease of suction is required to approach the main drain branch of the water retention curve, starting from a void ratio 0.6. So the bidimensional graph given represent a cross section of the void ratio at constant void ratio, of the water retention curve into the three-dimensional space. So by considering this, we can justify that the suction decrease because we had to reach a point, the point B, with a lower void ratio. So of course the state of the hydraulic state of the sample is forced to move down. If we can see another sample with a similar initial void ratio, initial suction, but consolidated at 800 kPa, also in undrained condition, what we can say? We can say similar consideration. The hydraulic path is given in these pictures. We are again in undrained condition. The points A and B represent the begin and the final points of the shearing phase performed in the suction control triaxial test, and again we have the both main drying and main wetting branch of the water retention curve at the void ratio close to what was estimating at the end, at the beginning of the shearing phase. During the undraining shearing, the sample show a volume reduction followed by a dilatative response. Since the shearing was performed again in undrained condition, the stress path is again vertical. The initial state of the sample is the point A, and lies close to the wetting branch, this line, because of the inhibition imposed after the consolidation during the test. So, based on the saturated soil mechanics under constant water content condition and dilatative behavior, the pressure are expected to lower, to decrease, and this happens even under unsaturated condition, starting from the wetting branch. In fact, during the undrained shear, the hydraulic paths move upward to reach the main drying branch with a void ratio is a little bit higher than to the initial void ratio, so this is in accordance with the dilatative response observed for the sample, even if the critical state was not completely reached in this case. Finally, it's possible to to see another sample with another initial void ratio, 0.8. Another suction, a higher suction was imposed at this sample, but what is important that this sample was shared under drained condition. The hydraulic path of this sample is given in these pictures at the top. Points A and B represent again the start and the final points of the shearing phase performed in the suction control triaxial test. And again, we have the main drying and main wetting branches of the water retention curve. Because of the drained condition imposed during the shearing, we are we have an horizontal stress path, so we have an horizontal line. The initial point A is quite close to the main drain branch, but during the shearing phase, this sample show a pure contractive behavior, as we can see here. So the void ratio decreases. So because of the drained condition and the contractive behavior, this sample lost some waters, but the volume reduction is greater than the exchanged water volume. Therefore, the hydraulic stress path moves accordingly toward the main drying branch. Finally, I would like to conclude with another application where we evaluated the soil compressibility, again of Stava tailings, and where the water retention curves gives us some important information to interpret this. As for the other parts of the lectures, you can see the result that I will show you in these two papers published with some of my colleagues on the University of Applied Science and Arts of Southern Switzerland, and published. In particular, this final application involves an experimental campaign of conventional odometer tests carried out on the same Stava tailings. The dependence of one-dimensional normal compression line and compressibility on the saturation state and preparation method is evaluated and interpreted, accounting again for the water retention curve. This is the apparatus we use. As I said before, we performed an experimental campaign at the University of Applied Science and Arts of Southern Switzerland on a statically compacted specimen, 50 millimeters in diameter and 20 in height. We tested the Stava samples with a different void ratio and different initial degree of saturation. The odometer tests on unsaturated samples were performed under constant water content condition and are compared with previous experimental data, in particular with data of the same Stava tailings under saturated condition performed some years before by Carrera, and with the result of a remolded specimen prepared by myself some years before in Politecnico di Torino. Here, the list of the sample. The sample in nearly saturated condition we test at SUPSI, and in unsaturated condition, with details in terms of initial void ratio and the degree of saturation, together with the preparation technique of the saturated specimen from the previous experimental campaign. As preliminary efforts, we can say that the suction level reached by unsaturated sample during the conventional odometer test was evaluated from the water retention curve, as we can see in these pictures. In fact, the knowledge of water ratio allowed to define a vertical hydraulic stress path, because, as I told before, we are in unsaturated, in a constant water content condition. The hydraulic paths cross the water retention curve main wetting branch evaluated at the void ratio reached during the decompression test, when 1D normal compression line could be identified. So the suction level can be obtained as practically as an average value of two points. Here we can see the suction level reached by the nearly saturated sample and by the unsaturated sample during this experimentation. All the tests performed in a saturated condition are given in these pictures on the left. Results obtained by Carrera on statically compacted sample are given by the black curves, this one, while the red curve is referring to the test performed by me on reconstituted samples. And I can stress, we can see the two set of curves converge toward a unique one-dimensional normal compressive line without any regards on the sample preparation technique. If, on the other hand, if test performed on statically compacted, nearly saturated sample, the green line, are plotted in the compression plane together with statically compacted, fully saturated samples, this one, we can see a certain transitional behavior, because we have 1D normal compression line parallel with the same slope, but parallel. So we can say that there is a certain transitional behavior, and this aspect, the motivation, the justification of this need further investigation. Finally, according to the Barcelona basic model, an increase of the compressibility index can be observed as the matrix suction decrease, as shown in these pictures for the different sample, with suction evaluated again from the water retention curve. Now, if just the effect of the saturation on the soil compressibility are analyzed, for instance, sample initial void ratio 0.528, the red line, and the other sample given by the purple line can be considered. They have a similar initial void ratio, but they differ for their initial water content. The compression index decrease from 0.059 to 0.049 when the water content increase. So the variation of the compression index is supposed due to the relevant change of the soil stiffness with the water content reduction. And on the other hand, if the effect of the density of the soil compressibility is studied, for instance, by considering the sample given by the red line and the sample given by the blue line, we can see that they have quite a similar initial water content, but different void ratio. So the compression index increase when the initial void ratio increase. In this case, this could be mainly due to a decrease of the soil stiffness with density reduction. Again, all this consideration can be done by considering the suction given by the water retention curve. I conclude my presentation with these final results. In particular, it was found that from the experimental result that the compressibility index, a function of the suction, as we say before, the values of the compressibility lambda decrease with increased suction. And the Barcelona basic model was adopted to get the theoretical compression index based on the experimental data we obtained. A fast decrease of the compression index can be associated with the suction increase until reaching asymptotic values. And again, these data on tailings are in a good agreement with data obtained in more standard soil. I mean, in soil not coming from mining operation. So I can conclude my presentation with some consideration. First of all, the tailing dams, because of their complexity, they need a very in-depth investigation during all phases, from the design, from closure, from operational times, and so on. Due to the hydromechanical coupling in unsaturated condition, the hydraulic response of tailings affect the mechanical response of tailings, and so the stability of tailings dams in terms of shear strength properties, as we saw at the beginning of these lectures. Unsaturated silty tailings were analyzed through the water retention tests, the suction control odometers, of course, and the effect of void ratio, fine content, and the preparation, sample preparation method on the water retention capability of Stava tailings have been investigated, and the results are given. Given the interaction between the hydraulic and mechanical response, the water retention curves seems to define a domain where the hydraulic pots could occur, and the volume change were studied and explained using the concept of the water retention curves. Finally, the dependence of the compressibility behavior on the saturation state and preparation techniques are presented, are evaluated and presented, and interpreted, accounting for the water retention curves, providing a full set of data for a complete characterization of Stava tailings. I wish to thank Geotecnia Brasil at the end of my presentation. I'd like to acknowledge to thanks Felipe Sousa from Geotecnia Brasil Group, the chairman Gino Mal Calderon for making this event possible and for giving me this opportunity. I wish to thank Professor Guido Musso from Politecnico di Torino, since he was my supervisor and my co-author of some papers whose results have been presented in these lectures. And I would like to thank my colleagues of SUPSI, in particular Dorota Chersky, as my co-authors of, again, some papers which results have been presented in these lectures. Finally, thank you all for your attention. I am now available to answer some questions, and here there is my mail address. So in case you can also write me, and you can discuss in more detail some aspect you are interested in. Thank you all for your attention.
Okay. Thank you, Dr. Gianluca, for delivering such an insightful and comprehensive presentation.
Thank you, Gina.
This topic is of great importance for our geotechnical community, especially those involved in tailings dam. I have some questions about this topic.
Yes, of course. You're welcome.
Can unsaturated tailings be susceptible to liquefaction?
Yes. In my experience, is are susceptible of static liquefaction, because we are static liquefaction is usually recognized as a phenomena which involves usually sand, so the coarse fraction, under saturation state of saturation condition. But I turn at the beginning of my presentation. But in other studies, we demonstrate that also the finer fraction of the tailings in nearly saturated condition are prone to static liquefaction. As I show at the beginning of this presentation, can you see also my screen? Okay, perfect. This is a test, conventional tests applied on the same Stava tailings in a conventional Bishop and Weasley triaxial test. We test samples at a different degree of saturation by imposing different B parameters, and if we plot the degree of saturation together with the B Skempton parameter, where the degree of saturation and B relationship has been retrieved from this formula, we obtain a behavior like this. And what can we say? We can say that if we move from fully saturated condition to little bit unsaturated condition, I mean, so for instance, 90%, so and not a big change in degree of saturation, we can see a very big decrease of the Skempton parameters. Since the Skempton parameter is related to the excess of pore water pressure, a big change in a big decrease in the Skempton parameter will result in a big decrease in the excess of pore pressures. So tailings would be less prone to static liquefaction, of course, because the excess pore pressure is not so high, so the effective stress is not zero. And you can find this result in a paper. I can share the paper with you, published last years, with details of this consideration, and also with details with how the static liquefaction of the samples is not only influenced by the saturation state, but also by the sample preparation technique. In fact, we try to perform tests with a sample, with compacted sample, or sample compacted, with the moist tamping technique on or different preparation method, and we see that the static liquefaction, the moist tamping technique gives the main susceptibility at liquefaction respect to other technique. Despite this could be a countersense, but despite sample with prepared with the moist tamping technique are denser than tubes prepared with other technique. So there is a combination. I believe that the static liquefaction is, of course, a combination between the unsaturated soils, the density, of course, above certain values, and for testing experimentation, the sample preparation plays a very relevant role in this. I hope to answer your interesting questions, Gina.
Yeah, of course. Thank you very much.
I can share the paper with you, and we can eventually discuss in more detail if you need.
Okay, thank you. I would like to have some question more, if it's possible.
Yes.
Well, I have two questions. Well, the second is there a connection between the air entry value and the liquefaction susceptibility of unsaturated tailings?
Okay. Thank you for your questions. It's interesting questions. At the moment, I not investigated this aspect. What I can see, just go up with the presentation so we can be supported by a graph. Just a moment, I can try to. Okay. This question would require some investigation, as far as I know. And what we can say about the static liquefaction and initial void ratio is this: that of course static liquefaction is more prone for loose specimen, and loose specimen are the specimen with the lower higher entry value. So just basing on this consideration, I would expect, but it needs some investigation more, that the susceptibility of static liquefaction can be could be correlated with the inverse, so the decrease of the air entry value, I think. But this is a good suggestion for further consideration and investigation, of course. Thank you.
Yes, thank you. And the last one is, how difficult is to calculate settlements in tailings storage facilities that experience unsaturated conditions? How about the volumetric deformation in unsaturated condition?
Yes.
Mhm.
The topic, the question is not easy, because of course from the experimental point of view, of course the change in the change of volume in saturated condition is related to the change of water. So we have when we measure some water coming out from a sample, okay, we can say that this volume of water corresponds to the reduction, of course, of the total volume, because all voids are full with water. This is not easy in unsaturated states, and this is because this is the reason I go up with my slide. Okay, this is because we use this apparatus, laboratory apparatus, the suction control triaxial test, where we can evaluate the water coming out or in from the sample during the test, and we can compare the water with the variation of the volume. The variation of the volume are taken from the laser scanner that can be performed by interrupting for 1 or 2 minutes each phase of the test, and to get the total volume. So the difference, by considering that the volume of solid is uncompressible, the difference of this volume, the total volume read by laser scanning, and the volume exchange and measure by volumeter is the difference in unsaturated condition. This difference is the volume of the air. This in laboratory. Of course, these apparatus are quite complex and time spending. So the use of these tests is not so common because of many technical difficulties. For example, the sample, the assembling of the sample, the sample could have been tested with a certain water content giving a certain apparent cohesion. If not, the sample could collapse and so on. So performing these tests for evaluation, also the volumetric soil response, is not easy. Totally different is the evaluation on site. The settlement of the tailings on site is quite difficult, as far as I know. And I know that some, for instance, some causes of tailings dams collapse could be due to the settlement experience at constant load. I mean, creep phenomena that are difficult to identify. For example, some consideration about these are given by Morgenstern and Price for a panel expert when we studied the Feijoa dam collapse and talking about satellitary images for the evaluation during the times, the deformation of the tailings dams with the time. So this is, as far as I know, in terms of in situ measurement, it is not easy at the moment. The microphone, please.
Yes, thank
Okay.
you. Yeah,
Okay.
of course, it's very challenging to calculate this deformation in saturated material.
Yeah, of course, I completely agree.
Yeah, and so thank you, Dr. Gianluca, for your excellent presentation. We are truly grateful to have had the opportunity to learn from your expertise today. On
Thank
behalf of
you.
the Geotecnia Brasil channel team, I would like to express our sincere appreciation for your insightful responses to our question and for contributing to our geotechnical community. Thank you.
Thank you all for giving me this opportunity. Thanks. Bye.
Okay, thank you.